Hello everyone, this is Professor Roman. Welcome to the 22nd video in my video lecture series, An Introduction to Discrete Mathematics. In this video, we are going to discuss unordered arrangements of elements with no repetitions, which are also known as combinations. So here is the formal definition. Let S be a set of size n. A subset of S of size k is also referred to as a combination of size k, or a k combination taken from the set S. I didn't use the term k permutation in the last video, but it would have been a good idea if I had, just to be consistent with k combination. A k permutation is a permutation of size k. I'm going to denote the number of k combinations taken from a set of size n by Cnk, with common notation, and analogous to Pnk. Now, just to be clear, combinations are nothing more or less than subsets, but it's a term that is used most often in combinatorics. Okay. So I will use either the term combination or subset interchangeably. For purposes of comparison, I'm going to make a list of the permutations and the combinations of a given size. So let's take the underlying set 1, 2, 3, 4. The permutations of size 3 that involve the elements 1, 2, 3 are these 6 right here. When we disregard the order and look at these as unordered arrangements or subsets, all 6 of these permutations collapse into a single combination. Same thing for these other groups. So that's going to give us a hint, which we'll talk about in a minute, on computing the number of k combinations from the number of k permutations. Okay, there's a simple formula. There's a map here from combinations to permutations, where this combination is mapped to these 6 permutations. This is a 1 to 6 correspondence, which means there are 6 times as many permutations as there are combinations, or put another way, the number of combinations is 1/6 of the number of permutations. Okay. Just to remind you, we talked about the 1 to k counting rule quite some time ago, so here it is again. Let A and B be finite sets. If there is a 1 to k correspondence from A to B, then the size of B is k times the size of A. And I called that the 1 to k counting rule. Okay, and so that's what's going on in this case, a 1 to 6 counting rule. There are 6 times as many permutations as combinations. Now, before I generalize that, I want to introduce the concept of a binomial coefficient, which is something you may very well be familiar with because they appear in the binomial formula. So if k is an integer between 0 and n, the binomial coefficient, and this is read n choose k for reasons I'll discuss shortly, is defined by n choose k equals n lower factorial k divided by k factorial, which has this very nice symmetric formula in terms of factorials. N factorial divided by k factorial times n minus k factorial. Now, what's going to come up is that we're going to encounter integers that are not in this range. So these will be degenerate cases, and the definition, the convention, is that if k is bigger than n choose k is 0, if either n is negative or k is negative, and choose k as 0. These are merely conventions that will turn out to be convenient. Okay, theorem. The numbers CNK and PNK are related by this formula. Okay, this tells us that there are k factorial times as many permutations as there are combinations. And so we want to solve this for CNK. K factorial goes in the denominator. And since P and K is n lower factorial, is equal to n lower factorial k. When I said is, I didn't mean to say they're the same. They're not the same, as we've discussed. P and K is defined as the number of permutations of size k taken from a set of size n. N lower factorial is k is strictly an algebraic formula. But these two are equal, and so CNK is equal to n choose k. Okay, and just to be clear, I'm sorry if this is belaboring the point, CNK is defined to be the number of combinations of size k taken from a set of size n. And choose k is defined to be n factorial over k factorial times n minus k factorial. And this theorem says those two different expressions are equal in value. And here's the number of combinations of all sizes taken from a set of size n is the sum of these binomial coefficients. K goes from 0 to n, and that's equal to 2 to the n. We already know how many subsets there are of a set of size n, namely 2 to the n. So this formula follows from the first part of the theorem. To prove this, I've in a sense already explained how, let S be a set of size n. The function that maps a given k combination of S to the set of all k factorial permutations of these same elements, little a1 through little ak, is a 1 to k factorial correspondence. From the set of all k combinations of S to the set of all k permutations of S, of which there are n factorial. Okay. So the 1 to k factorial counting rule tells us there are k factorial times as many permutations as there are combinations. Then we divide by k factorial. Now I say the binomial coefficients are, well, I guess arguably, the single most important numbers in all of combinatorics. Okay. They've been around for, let's say, about 1,000 years, give or take. There are, in some sense, whole books written on binomial coefficients. Again, this symbol is read n choose k as a reminder of the number of ways to choose k elements from a set of size n. Okay. And this language is really useful when it comes to solving counting problems that involve binomial coefficients. For example, one of the things I do in my elementary classes is I talk about poker hands. How many flushes are there? How many straights are there? How many full houses? And so the way you determine those numbers is to pretend you're constructing, let's say, all the possible full houses. If you're not familiar with poker hands, a full house consists of 3 cards of the same denomination, like 3 kings, and 2 cards of the same denomination, like 2 eights. And the way you count that is you say, how many possibilities are there for choosing, that's the operative word, choosing 3 kings from a deck of cards, and also how many possibilities are there for choosing 2 eights from a deck of cards, and you use the fundamental counting principle. So it's a matter of choosing a certain number of elements from generally a larger set. And if you think in that language, it will help you with the binomial coefficients. In evaluating binomial coefficients, we can use any of these expressions, but just as with permutations, the expression that's all factorials is a bit dangerous because these factorials get large so quickly. This formula here, which still involves k factorial, will hopefully cut down on the arithmetic. So it's in general going to be the most efficient way to calculate binomial coefficients. Here are some examples. I'll let you look at those. This group of binomial coefficients is worth memorizing. The first one, n choose 0, is 1. You don't really have to memorize that. How many ways are there of choosing no elements from a set of size n? Just one way. You don't choose anything. End of story. N choose 1. How many ways are there to choose one element from a set of size n? Well, you got n choices. N choose 2 is this value. N choose 3 is this one. So n choose 2 is definitely worth memorizing. And I think you might profit by memorizing n choose 3 as well. Since the evaluation of binomial coefficients is so important, since these coefficients are so important, there's been a lot of work on, in the last, say, 1,000 years, that going into deriving formulas that relate various binomial coefficients. I have a book. It was published by an author, a mathematician, I don't know, 60 years ago, something like that. And it's a paperback, and it's a couple hundred pages, and it's just formula after formula. That's all. It's just a reference book. So there are thousands of formulas relating binomial coefficients. There are a handful of them that are quite useful. I'm going to talk about some of these in the next section, so that probably the next video. The simplest one, however, is this one. Well worth remembering. And all you have to do is write down the definition using factorials, and you'll see they're the same. But there's another way to see these two binomial coefficients are the same without writing down anything. This is the number of ways of choosing k objects from a set of size n. But there are 2 ways you can do that. One is to imagine a box with n objects in, and you want to choose k of them. You pull out those k, you put them on the table. There's another way to do that, and that is to pull out the objects you do not want and toss them in the wastebasket, leaving the objects you do want. So this also counts the number of ways of choosing k objects from a set of size n, but it does so by choosing the ones you don't want, the n minus k objects you don't want, and ignoring them, throwing them out, whatever, and the remaining objects are your choice. Okay, that's worth thinking about. My description may have made it more complicated than it really is. Okay, but it is definitely worth thinking about until it's absolutely clear. And it can be very useful. 100 choose 2 is simply 100 times 99 over 2. That tells us immediately that the number of ways of choosing 98 objects from a set of size 100 is also 4950, because it's equal to 100 choose 2. Okay. More examples. The number of ways of choosing 3 objects from 4 is 4 choose 3, which is the same as 4 choose 1, which is 4. Number of subsets of size 95 taken from a set of size 100. 100 choose 95, which is equal to 100 choose 5, which is then most easily computed with this formula, 100 lower factorial 5. So you start with 100, 99, 98, and you write down 5 factors. The last one will be 96. And you divide by 5 factorial. The number of 5-card poker hands are always 5 cards, that can be formed from a deck of 52 cards is C 52 5, which is equal to 52 choose 5, which looks like this: 2,598,960 different poker hands. If you're familiar with bridge, a wonderful game, quite complicated, bridge hands consist of 13 cards. The number of such hands is C 5213, which is equal to 52 choose 13, which is 635 billion 13,559,600. It's a lot of bridge hands. A certain club has 5 male and 7 female members. How many ways are there to form a 7-person committee consisting of 3 men and 4 women? Okay, this is a typical counting problem involving combinations. There are C5 3 ways to choose 3 men from the 5 men in the club. There are C7 4 ways to choose 4 women from the 7 women in the club. Since those 2 tasks have the independence required to apply the multiplication rule, you multiply, you get 350. The number of ternary words of length 12 that have exactly 7 zeros, 3 ones, 2 twos, 12 choose 7. Once that's done, you've chosen from the 12 positions in the word 7 places, 7 positions in which to put the zeros. That's the first task. Second task, you have 5 open positions still. Choose 3 of them to place the ones. You now have 2 open positions you have to fill with the 2 twos. Multiplication rule applies. This is the number. Okay, here's a little more interesting problem. How many subsets of size 2 are there taken from this set, numbers 1 through 20, that do not contain 2 consecutive integers? So the subset can't contain 5, 6, or 8, 9, or 19, 20. Well, this is an example. It sounds like a little bit of a tricky problem, but if you look at it the right way, it becomes much simpler. And as we've discussed before, in this case, the simplest way to answer this question is to count what you don't want and subtract from the total number of subsets of size 2, C22, or 20 choose 2. Now, a subset of size 2 that does not consist of consecutive integers sorry, I said does not, I meant does consist of consecutive integers. This is coming to you in real time, so I'm going to make these blunders, as you've probably already noticed. A subset of size 2 that consists of 2 consecutive integers has the form k plus 1. K can be as little as 1, but as much as 19. So there are 19 such subsets. So from the total C22, 20 choose 2 subsets of size 2, you subtract the 19 that you do not want, that are not permitted, and you get 171. Okay. So if you had to address this directly, how many subsets of size 2 are there from this set that do not contain 2 consecutive integers? Well, you could say if one of the elements is 1, the other one could be 3 through 20. If let's say the smallest element, if the smallest element is 2, then you could have a 1 or 4 through 20, and you could break it down that way. And that's not that difficult, but it's a lot more difficult than the indirect way of counting what you don't want. The tip-off really is that there aren't very many things you don't want. Okay. In fact, there are only 19 possible subsets of size 2 that you don't want, whereas there are 171 that you do want. Okay. So it's easier to count what the small number that you don't want and subtract. It's this formula here, really, counting what you don't want. Okay, let's look at this example. How many ways can 12 people be partitioned into 3 groups of 4 people each? So let's denote the people by P1 through P12. Now we can reason as follows. The number of ways of choosing 4 people for the first group, say call it G1, is C12,4. The number of ways then of choosing 4 people for the second group, G2, is C8,4 because we've already chosen 4 people. We've got 8 people left. Finally, there are C4,4, one way to choose the remaining 4 people for group G3. And since this satisfies the required independence condition, we can use the multiplication rule, 34,650. However, there's a hidden subtlety here. We have assumed something that may not be applicable, and that is that the groups are distinguishable, that the first group is some ways different from the second, which is different from the third. They're not interchangeable. Let me give you a concrete example. Suppose that this was some sort of contest, and the first group of people are entitled to get $100 each. The second group of people get $50 each. The third group get $10 each. Do you care which group you're in? Absolutely. They are distinguishable groups. On the other hand, if the purpose of dividing the people into groups is simply to place each group in a separate but identical room, to listen to the same recorded but highly stimulating lecture in combinatorics, then it doesn't matter which person goes into which room. In a sense, the rooms, the groups, I'm sorry, not the rooms, the groups are indistinguishable. Okay. So there's a difference here in counting. If the question had been, how many ways can 12 people be partitioned into 3 distinguishable groups of 4 people each, then the answer is, as we said, 34, 650. Group 1 is distinguishable from group 2 and 3. We choose 4 people for the first group, 4 people for the second, 4 people for the third. If the groups are considered indistinguishable, we have overcounted. And we've overcounted by 3 factorial, by the number of ways of permuting those 3 groups. So think about this in terms of permutations and combinations, and it might become clearer. But it's important to spend some time with this notion of distinguishable and indistinguishable groups, because we're going to come back to it in the future, and it's going to get, let's say, a lot worse than it is now. So if you can get a hold of this issue and convince yourself, yes, the distinguishable the ways of partitioning the people into distinguishable groups corresponds, in a sense, to the permutations, whereas the ways of partitioning the groups into the people into indistinguishable groups corresponds to combinations. It will help you when we get to more sophisticated questions. Okay, I think that's enough for this video. There's some things here to think about. In the next video, I'll discuss properties, algebraic properties, combinatorial properties of the binomial coefficients. So thank you for watching, and I hope to see you in the next video.